Hi, welcome to When We Think Events Are Independent and They're Not. In this video, we're going to talk about the importance of distinguishing between independent and dependent events. We could give examples from physics, but instead we're going to look at examples from everyday life scenarios. Specifically, we're going to talk about how things can go wrong if you think events are independent when they aren't. We'll specifically look at the case where we think some phenomenon is described by the Poisson distribution when it actually isn't. We will focus on two ways that mistakes can happen. In the first type of scenario, we'll look at the case where we are making predictions about some phenomenon. Here, if we assume events are independent when they are in fact not, we can make very incorrect predictions. In the second type of scenario, we are making some observation and trying to draw conclusions from it. Here, if we assume events are independent when they are not, we can draw incorrect conclusions from our observations. Okay, let's briefly mention what knowledge would be useful for understanding this video. It will help if you've seen stuff about the Poisson distribution. There are a bunch of videos on this channel that can help with that, so you can check out the Poisson Statistics playlist. Here, we're just going to state, but not derive, the features of the Poisson distribution that you need for this video. Okay, with that, let's start with a very brief review of the Poisson distribution. Let's first mention what type of situation we need for the Poisson distribution to be applicable. We need some type of event which occurs randomly with a constant probability of occurring per unit time. These events happen at an average rate that we call R. And these events are independent. This means that an event occurring or not occurring at some time does not affect the probability of events occurring at other times. The Poisson distribution gives us the probability that exactly m events will occur in a given time interval t. The expression for that probability is given here in terms of the rate r, the time interval t, and the number of observed events m. Here are some phenomena that it would be reasonable to expect are described at least approximately by a Poisson distribution. Nuclear decay is well described by a Poisson distribution. If we have a radioactive sample, the decays of individual atoms are the relevant events. We could also look at meteorite strikes. Here, the events are the individual strikes. And we could also look at car accidents at a certain intersection over a given time interval. Here, the events are the individual car accidents. For example, let's say a certain intersection has, on average, 1 car accident per month. So, R equals 1 per month. We will look at the intersection over a given 3-month period. This means t equals 3 months, so RT equals 3. We can now ask a question like, what is the probability that the intersection has 5 accidents in this time? In other words, what is the probability that m will be 5? So we can take a look at the Poisson distribution for RT equals 3, shown in the plot on the right. We take a look at the bin for m equals 5. We can evaluate this using the expression for the Poisson probabilities. If we do, for RT equals 3 and m equals 5, we get about 10%. Now, the Poisson distribution has a standard deviation of the square root of RT. This gives an idea of how much M typically deviates from RT. Okay, now that we've reviewed the relevant features of the Poisson distribution, let's talk about what happens when events we think are independent actually aren't. We're going to start with the case where we incorrectly assume that events are independent, and this causes us to make incorrect predictions about some phenomenon. To do this, we'll make up a toy example involving a hypothetical insurance company. Okay, so let's imagine that there is an insurance company with the following features. It insures homeowners against fires. It issues policies over a certain geographic area. And it wants to predict how many house fire claims will be made in the month of July. Individual fires are in separate houses, so it's reasonable to think that they would be independent. The insurance company has records for the last 10 years. They find that they get N claims in the month of July on average. And while their data is limited, their July records for the last 10 years are consistent with a Poisson distribution where RT is set to N. So let's imagine what happens if the insurance company takes their claims for the month of July as Poisson distributed with a mean of N. If the claims for July are well described by a Poisson distribution, the number will vary with a standard deviation of the square root of N. So the insurance company very roughly expects that the number of claims will be between about N minus the square root of N and N plus the square root of N. But this is very rough. It would not be terribly surprising if the actual number of claims falls 2 or even 3 times the square root of N away from N. Now, let's imagine that a forest fire comes through the region serviced by this insurance company. The forest fire destroys multiple homes. The fires in these homes are most definitely not independent. This means that Poisson statistics do not apply in this case. The number of claims in July can easily be far outside the range of N minus the square root of N to N plus the square root of N. So our hypothetical insurance company needs to take into account such possibilities. Let's briefly mention a couple of related examples. We could have a store that stocks basic necessities. They know approximately how many of a given product they need to stock for a given week. But this can fail badly if, say, a coming storm causes a large number of people to suddenly want to purchase the same item. Alternatively, the traffic to a web server can spike if something goes viral. Suddenly a large number of people can all want to see the same content, possibly becoming aware of it from a single source or small number of sources. Okay, now let's look at another type of scenario. Here we're making some observation and using that observation to try to come to some sort of conclusion. Here, if we incorrectly assume that events are independent when they are not, we can draw incorrect conclusions from our observations. So let's look at another toy example. Here, shipping damage. Let's say you own a business. You sell some product which you buy from a manufacturer. You decided to change the shipping company which you use to order the product from the manufacturer. And you want to know if the new shipping company damages the product at a greater or lesser rate than the old shipping company. With the old shipping company, approximately 2% of the products arrived damaged. Every week, you buy a shipment of 100 units. This week, you use the new shipping company for the first time, and 10 units arrived damaged. How does this first week with the new shipping company compare to the old shipping company? Here, you assume that the breakage of the units is independent. So you're assuming the fact that one unit gets broken does not impact the probability that other units get broken. With the old company, 2% of units would get broken. So out of 100 units in a weekly shipment, you would expect 2 to get broken. This means RT equals 2. Here, 10 units were actually broken, so M equals 10. We can calculate the Poisson probability of 10 arriving damaged if, on average, 2 do. We plug 2 in for RT and 10 in for M, and get that the probability is 0.0038%. We can also ask for the probability that at least 10 are broken. Then the probability is slightly higher, 0.0046%. Since these are very small numbers, you conclude that the probability that the old shipper would have messed up this badly is tiny, and you resolve to switch back to the old shipping company. You mention that 10 of the 100 units in this week's shipment got damaged to your employee. Your employee responds, 10 arrived damaged? Yeah, that's pretty normal. The units are sent in packs of 10. A weekly shipment is 10 packs. About every 5 shipments, an entire pack gets damaged, and we lose 10 units. So what we have here is that with the old shipper, about 2% of units would be damaged overall. This is because about 1 in 50 packs was damaged. So when the units were damaged, they tended to be in groups of 10. So this outcome wasn't rare with the old shipper. In fact, it happened about once every 5 weeks. The breaking of a given unit is not independent of the breaking of other units, and the conclusion based on Poisson statistics was not justified. What we see here is that assuming that events are independent when they are not can lead to misinterpretation of data. Let's briefly look at a related example. Suppose you want to know the answer to some question. So you look up the answer from several sources, and they all say pretty much the same thing. It seems unlikely that they would all make the same mistake, so you figure that this answer is probably right. In this case, you're relying on the assumption that the different sources are independent of each other. But what if they all got their information from the same source? In that case, it would be pretty easy for all of the sources to be wrong in the same way. Okay, so to conclude, assuming events to be independent when they're not can lead to very big mistakes.